of this abstract of chapter 5 was the example, only for completion. And now we have the last chapter today, and I think after we finish this chapter 7, we will talk together with Professor Tim what to do in the next steps. That's chapter 7, the abstract of chapter 7. So what is chapter 7? What is not in the other chapters? We have already talked about all these things, but it is written down here. We talked about skin depth. And I talked about that, skin depth in millimeter is 50 cycles is 9.5 millimeters.
Yeah.
And then we guess it's 9 millimeters in Korea, 60 hertz. But here is written down 8.7 millimeters. And if you have not 50 hertz, 150 hertz, you have 5.5, and 1 kilohertz, you have 2.1. What is interesting for 150 hertz? If you have not sinus harmonics, you have, I don't know the expression in English,
harmonics.
The harmonics. And then you have for 150 hertz cycles, you have another suppression than for 50. Okay. And aluminium, if you try aluminium electrode arm, you will see that it's almost the same, almost. A little bit bigger, is it 12 millimeters and 11 millimeters. And graphite electrode, the graphite electrode, there is only an example of it. It depends on the conductivity of graphite. And the conductivity on graphite is depending on the temperature. And you can't say that the value is at 50 hertz, 160 millimeters. It may be more, it may be less. But if you have a big electrode, and you have 160 millimeters of that is almost of the area. The area is depending on R to the square, and so it's in the inner of the electrodes there is not so much area, and so you can for the graphite electrode maybe that you can say it's a full cylinder.
This table cannot consider temperature. Cannot consider temperature.
The conductivity and the resistance of all materials is depending on temperature. For a metal, you can say if you have 10 degrees difference in temperature, you will have 4% resistance derivation. 10 degree makes 4%. If you have 100 degree, you will have 40%. If you have 250 degrees, but copper doesn't work at 250 degrees. It's too hot. But if it would be, the resistance of copper will be the double, roundabout. And if for graphite, we don't know. There are different companies shows different values, and so we don't which temperature it's graphite at which place, and so the electrode is calculated as a full cylinder. So that was about
In this calculation, the base is base temperature.
At which that is a value which is shown in a list of a company which offers graphite electrodes. I looked for this, Professor Tim looked for this, and he got almost the same value. But there's a difference. What they say 0.14, the other says 0.28. It's copper is 56 conductivity, but graphite it depends on many things. Copper is a poor copper is 56, and if copper is not pure, the copper for water tubes, for example, has not 56 conductivity. It's another value, less than many less than 56. I don't know exactly. Maybe 10, maybe 5. Copper is only a conductor if it's electrolyte copper, if it's pure copper. So 7.1 and 7.2 belongs together. If you have an electrode plated copper plated electrode. Mr. Tim has some information about
under the bill.
Here the conductivity is named sigma, and in opposite to copper, graphite has a negative temperature coefficient, because with increase of temperature the conductivity becomes bigger. The reason is that in copper all electrons are free in the conductivity band of they are not atomic. They are not in the atomic. And here, by graphite, if temperature increase, more electrons become free and can transport the current. And you will see here 100 to 200. If you have 2,400 degrees, it's double than at 100 degrees. Yeah. And that means the skin depth is varying by temperature, because the conductivity is varying by temperature. You will see here's the conductivity, and it is in the formula, and then you will have another skin depth for the electrodes. Okay. That are some.
You can get this by SGL. SGL group. These are, they publish this.
I know. We cannot find this data where.
You cannot find it.
Yeah.
This is from the presentation of the company, SGL. Yeah. If you want to have a copy of this, we can.
Yeah. Take a picture.
Take a picture.
Yeah.
Oh, yeah. You want to have more? Graphite electrodes?
Yeah.
The total paper?
Yeah.
This the first part?
Yeah.
And this paper is in between.
요거 보고 좀
Yeah.
Aber es ist doch hilfreich ein bisschen sowas, ne?
Ja, sicher.
Ja.
좀 이따 찍자.
Yes.
Break time.
Yeah,
We'll take
you make
picture.
a copy. You can make a copy if you want. With a camera. Then we make coffee break also. Okay? Let me say, give me the paper, I will have the copy.
So, copper-plated electrode arm. For example, it's 300 millimeters, it's 500 millimeters. So, and so we have what we have here is we have 9 millimeters. This one, and so we put in 300 and 500 in the program, and we will say the copper is a strip-line conductor. The copper will only the current will only flow at the surface of outside of this.
This is how our program works. Yeah. We think the current is flowing at the surface.
Yeah.
Yeah.
And it's no different. It's a very small difference if you make the 10 millimeters more or 5 millimeters more here. So we say for program for reactance calculation, you only use the outside. If you want to correct, and this is the outside measures, then you can say that's the outside measures. We have 5 millimeters less here, we have 5 millimeters less here, and then you put in 290, 5 millimeters here, 5 millimeters here, and you have to put in here 490. And if you will do this and put it in the program and you will try, you will see that there is no big difference.
If you look into this table, you see the skin depth for copper is 9 or 8 millimeter. It does not help if you make the copper thicker. This does not help. It's only the current flowing at 9 millimeter. And there you also can choose 8 millimeter or 7 millimeter. It's your decision.
We talked yesterday about round conductors, that we have to if we have to calculate the GMR of a tube, that we have 150, 120, and then we have to say for GMR calculation we have to use here 141.
Yeah.
That we did yesterday.
Yeah.
And the day before already. Okay. That, but here it's stated. So, the next is, if the program has no parallel conductor, the formula is for parallel conductors. Yesterday we discussed.
Yeah.
And we make an example of this and put in not values, but we put in all the A, B, C, and so on, radius and so on. We calculated this. But what happens if we have this one? If we have this one, we don't have the formula for parallel conductors. What to do for self-inductance? For self-inductance we use the original conductor, because most of the inductance is self-inductance. 30%, maybe 40% is mutual inductance. And therefore, you have to say which is the longest conductor. The longest conductor is the original conductor then. And then we say, what is the, where is the middle point, and then we make it parallel. And then we can calculate not the red one, but the black one. Okay, and the next one is chapter 7.4. Chapter 7.4. We already talked about this, but here is the documentation of this. I think it's in the instruction manual too. I don't know, Mr. Tim.
What's that?
Is this picture in the instruction manual?
The picture, das untere?
Die beiden, ja, die untere. Die oberen nicht.
Oh, I do not change.
It's not important that
we have this picture.
Okay, yeah. If you have the flexible cable, yeah, you can't calculate round in circle or so on. You have to put it as 3 parts. And what is important? That important is that this length is the same as this length. And if this is correct, the self-reactance of this part is correct. And the mutual inductance or mutual reactance is only 40%, and if we put it here, it's not so much difference. Maybe that we have 2% error, but more not.
In most cases, this is a half circle on the left side. This is a half circle. In most cases, because you cannot put it together, because you must from the manufacturer, this is a minimum radius. You cannot make it smaller. Then this is going bad. Yes. But this is given by the manufacturer. And if you make a construction, you must look into the table of the manufacturer. He says, not less than this minimum distance.
So, for this, in all parts, you can put in 8 coordinates. For the flexible cable, you can only put in 1 coordinate. I think we have already seen it in the program. Why is it? Because the flexible cable has a begin and an end. And between this begin and end, but there is how we call it, a flexible cable, curved diameter, vertical length, splitting section. The flexible cable ends. There is, in German we call it Seilfahne, and we can put in this length and this length. This length and this length. We can put in, and this is another conductor. That means the flexible cable for the program has 1, 2, 3, 4, 5 conductors. the GMR of this 3
Yeah.
is the same, and this has we calculated different. But it's not a big length, so the inductance is small. So, and now to the left, to this one.
This one, yeah.
No,
Or
no,
before this.
I will make it this one. No,
Before this.
Yeah.
Previous page. And three page. Three page.
Ah.
I have questions.
so.
We are operating the UAF, in this case, cable. What could cable is some vibration.
The vibration of the
Yeah,
cable.
yeah. So in this case, mutual reactance is some in length is different in cross and.
I think there are no vibrations of the cable, there are more vibrations of stiff systems. If you have tubes on the arms, they can vibrate, and the electrodes can vibrate. But I don't think the other cable may be moving slowly. This is dependent from the electromagnetic forces between the system. We can speak about the electromagnetic forces. You have big currents and you have strong fields, and if you have an electric, this may be an electric conductor is in a field, you get forces. And most important, the forces are for the electrons, because some electrons begin to vibrate, and you can get electrode breakages. I have worked very long years about the reason of electrode vibration. What is the reason for this vibration? Bang! It's over. But I think there may be forces between, if you have 4 cables in one phase. They are, I think, connected together. Combined together. And therefore they try to give the system a special distance, and I will try to find a picture where we can see that. But vibrations of electrodes may be very, very few, very, very low frequency. But important and dangerous are the high frequency vibration of electrodes, and you can also have vibration because of forces between these tubes. They are very big, and you can also have eigenfrequencies of these tubes, and if the forces have the same frequency than the eigenfrequency, this is bad. This is very bad. And this is the advantage of current conducting arms. They do not have eigenfrequencies. It's not important. Yes. You see here the flexible cables have a special distance. They should keep this distance. And therefore they make rings about this. See, these rings.
Yeah.
This is a ring, yeah. Because they should have a special distance, not too close together.
Yeah, that's right. I understand this situation. We are calculation the reactance.
Yeah.
In this case, first important point is distance.
Yeah.
So one phase is two cable. Use the two cable,
Yeah.
and phase 1 and phase 2 is we consider two ranks.
The forces are
Yeah.
if you have two
Yeah.
cables of
Yeah.
different phases,
Yeah.
they are put
Yeah.
together.
Yeah. That's one.
Make this in cables,
Yeah.
in flexible cables.
Yeah.
The special vibrations of special frequencies. This may dependent from changing special changes in the current. The current is responsible for forces. The current there, and if you have fluctuations in the current, everything, the total furnace is vibrating. It's important which vibrations can be dangerous. And the most important forces and vibrations are dangerous for electrons, because they do not have these stiffness electron. If you have a long electrode, if they begin to vibrate, this is very dangerous.
So, the last page of our presentation here. If I make it, Mr. Tim says that's wrong, because we don't have 12 flexible cables in one cable, because half of them are water pipes. He told me. I am not an expert, therefore this question I can't answer what Professor Tim answered. He is an expert in how work furnaces. I only can calculate reactances. So here's an example how to calculate reactances. We yesterday made it for up to 8. I think up to 6 or up to 8 cubes on a, and so we have 12 conductors, and we have to build. We have 12 to 12 makes 144, but that's easier, the lowest, because if you have one, and all of this round table have through the others the same. If you name this, so it's the same distance. So we have only to look for 12. That means from this here we have to calculate 12 G's, and of this 12 G's we have to multiply, and this multiply we have to the root 12 of this.
Mr. Alles, in this technical description of cables, they are going from 5 until 15 cables in each special cables in each cable. Yeah, and there's also 12 is existing here.
But it's not necessary that you calculate this. If you buy a cable, flexible cable, the customer
Yeah.
No customer, which will deliver this cable, he will tell you the GMR.
Yes, it's in the paper.
In this paper,
The GMR.
and so it's not necessary to calculate. But if you if you buy separate cables, you have maybe you have to calculate. But we already yesterday we have already talked about this. I think the GMR of this you can already calculate.
You can calculate it. It takes you 1 day. Yeah.
Oh no!
My God.
No, 2 hours is enough. The Bach formula, the lower formula is you can make in half an hour. So that was the last presentation for me. I would say now I will ask you: do you have questions? Do you have questions to this book, Theory of Reactance Calculation? I will now answer. So, if you have additional questions. But I already answered yesterday and the day before many questions. But if you have now questions, we will discuss this. Otherwise, we will talk about the program together with Professor Tim. What we should change of the program.
그래서 계속 물어봐가지고 지금 이렇게 체크하고 있어요. 예.
Können wir das einmal aufrufen?
Ja, gut, nochmal aufhören. Welches File einlesen von den?
Ja, ist egal. We have time enough to discuss with you. What are you? Do you have special questions to the program, which does not work, and you do not understand what happens if you make this? I will speak with you about some examples, and I have more examples than written in our manual. I have more examples and show for you, and you can also get the files. I have for 3 other examples. I have the files here. Yeah, you can have this. But we would like to speak to you about, do you have problems with the action of this? Machen Sie mal Configuration, also das ist ein Picture, oben rechts.
Controlling picture.
Idea. This is how I will speak to you about this construction and how to use it. But now we can speak together before Professor Ahlers is leaving us in the morning or at noon. Do you have questions? Do you have questions? You understand that we do not show the flow in the bath. Können Sie mal aufzeigen? Ja, wie in this design, in this picture, there's no flow and in the bath. Können Sie das mal?
Was wollen wir haben?
Den Fluss, wie fließt der Strom in den Bad? Ja.
Ach, in the bath.
Ja. Dann gehen Sie mal raus. Und gehen oben kommen Settings.
Ah, ja.
And you can see this is the flow in the bath. So gehen Sie wieder raus. You see, we think the current is flowing at the surface of the bath.
Yeah.
in a little depth. Yeah? And we also do not show for you and we do not calculate
So,
the,
yeah.
we do not calculate the current flowing in the arc. I have here a picture. You see here are 3 electrodes, and this is a flat bath, no forming slag. You can see here the arc. You see that? Here the arc. But this is the arc, here and here. But this picture is not correct. It's not easy to make this picture, because in most cases you want to have a forming slag covering the arc. But this picture shows the arc may have this diameter and it's so long. This is not correct. I will tell to you about the arc, what happens in the arc. Well, this is the electrode, this is the steel bath. And this is the arc. This is the ignition. We know from the arc the current density is 1 kilo per square centimeter. This is the current density in the arc. If you have 1 kiloamp, 100 kiloamp arc, the diameter is, the surface is 100 square centimeter. This is not very much. This may be not very much. But your eye does not see that, because your eye is making a mean value and the arc is moving very fast, is making 100 circles per second, and there the eye sees this is the arc. And also the arc changes the diameter with the current. If you have this is the current versus time, and this may be the maximum 100 kiloampere, then the diameter of the arc is 100 centimeter, 0. 100 centimeter, 0. The change in the arc. And this is the reason, because we do not have the calculation of the reactance of the arc. But this arc reactance has to be added for furnace operation. Therefore, during furnace operation, the reactance is higher than this in our program. Therefore, this is the short circuit reactance. If there's the electrode is digging into the bath. Is that clear what I say? Yeah? We will speak about the difference of the operation reactance during steel making in comparison to the short circuit reactance. We can calculate, and we can also this measure, this short circuit measurements. Okay? But do you have questions to the program? Please say questions. We have questions. You see also, können Sie das Bild noch mal zeigen?
Ich wollte mal eben noch mal zeigen, wo gibt man denn hier beim Lichtbogen for this calculation, operational calculation, you have to put in a factor, and these are some methods. Bowman has 3 methods declared, and no, that's not the best. There are 3 methods of Bowman, and you can. And other people say we want to have other, they have experience, and other companies calculate this in a form. But this means that the factor, that the short circuit reactance is multiplied with a factor.
And I will speak about you in a special lesson about this. And you also see, nehmen Sie das mal weg, da, das oben, das da. You see also, this is the reactance we have calculated in the furnace. There may be a little reactance of the arc. There's also reactance of the transformer. And if you have an additional reactor, you must add this. And also, in every time, if you have a long wire to the steel plant, and every part, this is the step-down transformer, 110 kV to 30 kV. This is the steel, the steel 30 kV or 20 kV, and every must be added if you make the calculation of the total electrical system. And we have only calculated this, but this is the main important. Okay? Okay, jetzt kommen Sie wieder mal. But please have questions. Können Sie nochmal das Bild zeigen von vorhin?
Ja.
Mit dem Hochstromsystem, was Sie mit dem Reaktanzprogramm gemacht haben?
Close. Ja. Ich mache das mal wieder zu. Ich probiere. Er hat was Falsches gedrückt, aber das ist auch egal. Das ist korrekt. Hence calculation. Read from data. Controlling pictures. Yeah. Now you see, I have made the settings. I have changed the settings. And in the next time you use a program, the same setting is used. But if I will now make settings set to all standard, then we will see the whole picture, which we this one.
You see, sometimes you will have questions. Where does a new system starting? Where is it ending? Oh, it ends in the middle of the system. You see that here. In the middle of the system, the calculation ends. The electrode starts here and ends here. It's the surface of the bars. And the flexible cables start here and end here in the middle. In the middle. It's only to the middle line. And also the additional reactor ends here and starts here. Yeah, you see that? Yeah. This is a reactor of about 1 square meter. Yeah, 1 square. This is the typical size of additional reactor.
Yesterday we calculated this one.
Yeah.
So, do you have questions to the program, which I have to, which we have both people, Professor Tim and I, have to discuss? That's important now.
I have a question to the program. What do you believe now? We do not, kannst du das Bild mal wegmachen? We did not speak very much about these calculation of the current density because we don't have any experience about this. This must you decide. The current density in different systems, in the cable or current in the transformer connection. We do not know electrode, arm, reactor. This may be too high. What is typical? We do not have any experiences about it. This, if you make a new electric arc furnace, you must decide what is. You see the current density of the electrodes is small because there's a big surface. Yeah, big area. Yeah.
The conductivity is less, and you have more area. So, otherwise we would change the place.
Ja, dann bin ich mal mein Rechner.
I will, if you have no question to me, I will shut down my computer and Professor Tim comes to this.
Fahren Sie aber Ihr Computer erstmal runter und dann mache ich das aus.
Ich kann das auch abziehen jetzt.
Nee, das mache ich nicht so gerne.
Achso, das ist ja.
Ja.
Das heißt, ich fahre mal runter hier.
Ist das noch ein XP-Rechner?
Ja.
Und der hält so lange?
Ja,
Ah, das ist ein Dell, nicht?
das ist ein Dell, ja.
Der hat eine ganz gute Lebensdauer, nicht?
Das ist mir auch schon runtergefallen.
Ja? Und er geht noch.
Ja, genau.
Also jetzt geht er aus, ja?
This is electrode. This is electrode arm.
Ja?
In real, electrode arm length is this, but calculation the reactors, we consider only this part.
Mr. Tim already told it goes to the middle.
Yes.
The electrode arms goes to the middle.
Yeah.
That is the electrode arm, and the electrode begins in the middle,
Yeah.
always in the center. And
Okay.
Okay?
Yeah.
This is for all connections of different parts.
Yeah.
Yeah, it starts and stops in the middle, the center.
Start is in the middle.
Yeah. It is not real in this case, but we can. Okay, das will ich mal ausmachen. Ja, geht raus.
hätte nicht die Kalifornien-Teile
Ja, doch. So. Das ist Ihr Computer, das ist Ihr Netzteil.
Das ist mein Netzteil, das nehme ich auch. All the yellow papers I have written, you can put in the waste box or you can take with you.
So, ich gebe mir mal Ihr Netzteil. So. Und dann will ich mal selbst anfangen. Ist denn der Herr Schubert ab und zu mal gekommen und hat Kaffee angeboten oder so?
Ja, die hatte mal wieder gefragt. Ich habe gestern auch meine Rechnung bestellt.
Ja.
Und die Dame ist heute Morgen gekommen, ob sie gleich Kaffee trinken soll. Ich habe gesagt, Viertel nach 10 Uhr.
쉬는 시간이
아,
Das gelbe Papier kann da liegen bleiben?
있잖아, 이거는.
Ja, wenn Sie es brauchen, gerne.
Ja, ich nehme es. Nimm das einfach mal an.
Ich habe zu Hause noch mehr.
Okay, das ist aber Ihr.
Das ist Herr Eons.
Alles Mr. Eon.
Nein, Mr. Jin.
May I have this?
Ja.
Oder?
Wollen Sie einen oder einen anderen Stift behalten?
Nein, ich werde mit dem Füller schreiben.
Ah, gut. Ich hatte
Ich
auch.
werde mit dem Füller schreiben.
Ich habe teilweise auch mit dem Kugelschreiber geschrieben.
This is a Chinese computer, I think. Why you? Sony
Sony?
is Chinese.
Made by Chinese.